Okay, let's unpack this. Get ready for a deep dive into a data structure that kind of takes the best of queues and stacks, gives you flexibility at both ends. Welcome to this deep dive.
Hi there. Yeah, today we're really getting into the double-ended queue. Most people just call it a dick, though, pronounced like deck,
It's
D-E-Q-U.
telling you a deck of cards. Got it. And for this exploration, we're looking closely at section 5.3 from Hello Algo. That's our main source here.
Right.
And our goal really is to go beyond just, a dictionary definition. We want you to really get what a deck is,
Mm-hmm.
understand how it works under the hood, why it's efficient, what you can do with it, and maybe see where you might actually use one so it really sticks.
Exactly, and it helps to place it, right? Talked about arrays, linked lists.
Facts queues.
Exactly, yeah, last in, first out.
Yeah?
And standard queues, first in, first out. The deck is interesting because it borrows from these,
Right.
but loosens the rules a bit.
Okay, so let's nail down that difference. What really sets a deck apart? A standard queue. That's like a line, right? Get in at the back, leave from the front.
Yeah, FIFO.
And a stack is like dinner plates, add to the top, take from the top, knifo.
Right. The big difference with the deck, and the diagrams in the source show this well, is you've got doors at both ends.
Open.
Yeah, it's still a line of things, a linear structure, but you can add stuff or take stuff away from the head, the very front,
Okay.
or from the tail, the very back.
Okay. So it's not just one way in, one way out, or even just one combined entry-exit point, like a stack. You've got like 4 options: add front, remove front, add back, remove back.
That's it, exactly. That dual access, that flexibility for adding and removing at either end, that's the core idea.
Flexibility. Got it. Okay, so if you have that kind of power, what are the main things you can do with the deck? What are the standard operations?
Well, the source lists them out nicely. For adding, you've got push first. That puts a new element right at the very front, the head.
Jumping the queue.
Yeah, exactly. And then there's push last, which adds to the tail, like joining the line normally at the back.
Makes sense. Adding at either end. What about taking things out?
Similar deal.
Hmm.
Pop first removes and gives you back the element that was at the head.
Takes the person who is next up.
Right. And pop last removes and returns the element that was at the very tail.
So like removing the last person who just joined.
Okay.
And I guess you can probably look without removing too.
Yep. Standard peak operations. Peak first lets you see what's at the head without changing anything.
Yeah.
And peak last lets you see the element at the tail. And of course, you usually have size to see how many things are in there. And it's empty to check if it's empty.
The usual housekeeping stuff. Now, you mentioned efficiency earlier. This sounds powerful, having all these options, but is it fast? Because, flexibility isn't much good if it takes forever.
Now that's the really cool part. This is where the Deque goes from just being flexible to being, well, incredibly useful. The key thing, the thing that makes Deque so valuable, is that all these core operations we just talked about.
The pushes, the pops, the peaks.
Yeah, push first, push last, pop last, peak first, peak last. They're typically designed to run in O1 time.
O1, constant time. For those maybe less familiar, just remind us what O1 means here.
It means the operation takes basically a fixed amount of time. It doesn't matter if your Deque has 10 elements or 10 million elements. Adding to the front, removing from the back, it takes roughly the same, very small amount of time.
And that's huge compared to, say, adding to the front of a regular dynamic array, right?
Oh, absolutely. Adding to the front of a standard array usually means shifting everything else over one spot. That's O(n). The time grows with the number of elements, n. Same problem if you remove from the front of a basic array.
So the Deque promise is O1 at the front and O1 at the back, efficient access at both ends.
Exactly. And that's why you see built-in deck types in lots of languages. Python has collections.deque. C++ has std.deque. Java has the Deque interface, often using ArrayDeque or linked list.
And they might have slightly different names for the methods, like the source shows.
Yeah, you'll see append left and pop left in Python, or push front and pop front in C++ there, or offer first and pull first in Java. Different names, but the same O1 goal for both ends.
Okay, that performance is impressive, but how? How do they pull off that O1 magic at both ends? What's going on under the hood? The source mentions 2 main ways, right?
It does. Like regular queues, decks can be built on different things. The 2 main strategies aim for that dual-ended efficiency.
Let's take the first one, using a doubly linked list.
Okay, so remember how a standard queue works pretty well with a singly linked list?
Yeah, add a tail, remove from head, easy O1 if you track both ends.
Right, but the problem with a singly linked list is removing from the tail. You have to walk all the way from the head to find the node before the tail to update its next pointer. That's slow, O(n).
And a dake needs fast removal from the tail, too. Pop blast.
Exactly. And that's why a doubly linked list fits perfectly. Each node doesn't just have a next pointer. It also has a prev pointer pointing backwards.
Ah, okay. Like
Yeah.
two-way streets between nodes.
Precisely. And you keep track of the very first node, let's call it front, and the very last node, rear.
So if I want to push first, I make a new node, point its next to the current front,
Okay.
point the old front's prev back to my new node,
Right.
and then just make front point to the new node.
You got it. All O1 pointer juggling.
Yeah.
Push last is basically the same logic, but using the rear pointer and the next pointers at the tail end.
And pop first is just moving front one step forward using front dot next.
Yep. And maybe nulling out pointers on the old head. Again, O1. And now, the key part for the deque, pop last.
Okay.
You have the rear pointer, so you know the last node instantly. And because it's doubly linked, that last node has a prev pointer that takes you straight to the second to last node.
Ah, no need to traverse.
Exactly. That second to last node becomes the new rear. You just update its next to null, update the main rear pointer, and you're done. O1.
Wow, okay. The prev pointer is the hero for pop last. That makes total sense why a doubly linked list is a natural fit. It gives you that O1 backward step from the tail.
It really does. The whole structure, front pointer, rear pointer, next pointers, prev pointers, it all works together to make those core deque operations constant time.
Okay, doubly linked list implementation, check. What about the other way? The circular array? That still feels a bit counterintuitive for front operations. Arrays usually mean shifting.
You're right to be cautious. A standard array, where index 0 is always a start, would definitely be ON for adding or removing at the front. The trick is to treat the array space as circular, like a ring.
A ring buffer.
Yeah, exactly. The logical front of the deque isn't stuck at index 0. It can be anywhere. And when you go off one end, you just wrap around to the other.
Okay, how do you manage that wraparound cleanly?
Usually with, well, math. You have the array itself, let's say nums. You have an index, front, that tells you where the first element currently is in the physical array. And you need a size to know how many elements there are.
Right.
The key is calculating physical array indices using the modulo operator, %. If the array has a capacity of, say, 10, and your front is currently at physical index 7, and you want to push, first you need to put the new element before index 7. Circularly, that means index 6. If front was 0, before 0 would wrap around to index 9.
So you calculate the new front index, maybe using something like front 1 plus capacity, % capacity.
Exactly that kind of logic.
Yeah.
Calculate the new front index, put the element there, and increment the size, all O1.
And push last, adding to the back.
That goes in the slot after the current last element.
Yeah.
You calculate where that index would be, again using modulo arithmetic like a front plus size % capacity, put the element there and increment size, O1 again.
And pop first just means moving the front index forward circularly, like front
Yeah.
plus 1% capacity and decrementing size.
Spot on.
And pop last.
You just decrement size. The element is still technically in the array slot, but is no longer considered part of the deque. The next push last would overwrite it. The logical removal is O1.
The circular array approach feels pretty clever,
Yeah.
using modulo to fake an infinite loop. Does this also give O1 for everything?
Yes, if it's implemented properly as a dedicated circular array structure for the deque. And this is a really important point the source makes, something to watch out for.
Oh, what's the catch?
The catch is when you don't use a dedicated deque class. Language-provided ones, like Python's collections.deque or Java's array-deque, they're usually built using optimized circular arrays, or sometimes linked lists, and do give you that O1.
Okay.
But if you just take a standard dynamic array in, say, JavaScript, and use its built-in unshift method to add to the front, or shift to remove from the front,
Yeah.
those methods on a standard array might not be O1. They might still be doing the ON shifting behind the scenes because the underlying structure isn't necessarily a circular buffer. Same potentially for Swift's insert at 0 or remove first on a basic array.
Ah, that's a super important distinction. So just because a method looks like it does a deque operation doesn't mean it has the deque's O1 performance if you're just using a regular array type.
Exactly. You need to use the language's actual deque implementation, or be sure the underlying array method is specifically optimized for O1 front operations, which is less common for general purpose arrays.
So rely on the dedicated deque classes if you need that guaranteed O1 at both ends. Don't try to fake it with standard array methods unless you know for sure they're optimized.
That's the safe bet, yes.
Yeah.
Using standard array shift unshift is likely to bite you with performance issues as your data grows. A proper DIC avoids that.
Okay, this is great. We know what it is, what it does, how fast it is, and the two main ways it's built, the doubly linked lists or circular arrays with that important nuance. So let's tie it all together. Why does this matter? Where would you actually use one of these?
Well, its versatility is the main thing, since it can do stack things, push last post, and queue things, push last pop first efficiently.
All right.
It can handle use cases for both. But where it really shines is when you need something more, maybe combining aspects of both or needing that flexibility at both ends simultaneously.
And the source gives a really concrete example. Implementing undo, but with a limit.
Yes. This is a perfect application to see why you'd need a deck. Think about a simple undo function in like a text editor.
Okay.
Usually it's a stack. You type A, push type A onto the stack. You delete a word, push delete word onto the stack. Click undo, pop the last thing off and reverse it. Oh, a foe.
Makes sense. Undo the last thing you did.
But real software usually limits the undo history, right? You can only undo the last, say, 100 steps.
Yeah, you can't undo forever.
So what happens when you have 100 actions on your stack and you perform the 101st action? You need to add the new action, but you also have to get rid of the oldest one to keep the history size at 100.
The oldest one. That's the one at the very bottom of the stack, the first one you pushed on.
Exactly. Which, thinking structurally, is the element at the front if you viewed that stack sequence as a queue.
Okay, so the problem is, how do you efficiently remove the item from the bottom of a stack? Standard stacks don't let you do that quickly.
Right. No pop bottom. That's O1. And a standard queue lets you remove from the front, pop first, but it doesn't give you the efficient pop last you need for the main LIFO undo behavior.
Uh-huh. And this is where the deque comes in.
This is exactly where it comes in. You use a deque to store the undo history.
Okay.
When the user does something, you push last the action onto the deque. That acts just like pushing onto a stack. The newest action is always at the tail.
And when they hit undo.
You pop last,
Mm-hmm.
that removes the newest action from the tail, just like popping from a stack. The core undo logic is pure stack behavior using the tail end.
Okay, but the limit, when the deque gets full.
Right. Before you do the push last for the 101st action, you check if the deque size is already at the limit, 101. If it is, you first call pop first.
Removing the oldest item.
Exactly. Pop first efficiently removes the element from the head of the deck, which is the oldest action, the one at the conceptual bottom of the stack history. Then you do the push last to add the new action.
Wow. So the deque is acting like a stack at the tail end, push last, pop last, for the undo-redo logic.
Mm-hmm.
And it's acting like a queue at the head end, pop first, just for managing the history limit. And because both ends are O1, the whole thing stays fast.
That's the perfect tool for the job. You need the stack's LIFO at one end, but you also need the queue's FIFO removal from the other end to manage the constraint. Only a DIC gives you both efficiently.
That limited undo example really nails it. It shows exactly why you'd need efficient operations at both ends. Cool.
Yeah, understanding the strengths of different structures lets you pick the right one when problems get a bit more complex like this.
Okay, awesome. Let's do a quick recap then. We defined the double-ended queue, the DEC, key feature, add and remove efficiently from both head and tail.
We stress the O1 time complexity for those core operations, which is crucial for performance, especially compared to trying the same on standard arrays.
We looked under the hood. Implementation via doubly linked lists, where the prev pointers are key for O1 tail removal.
And implementation via circular arrays, using modulo math to wrap around, but with that important warning about relying on dedicated deque types versus standard array methods.
Right, the performance nuance. And finally, that great limited undo example showing how the deque combines stack-like behavior at one end with queue-like removal at the other to solve a practical problem efficiently.
I think the main takeaway is really about efficiency. It's not just can a structure do something, but how fast can it do it? If you see a problem needing quick access or changes at both ends of the sequence, the deque should definitely pop into your mind.
Absolutely. So next time you're coding and dealing with a sequence where things need to happen quickly at the start and the end, remember the deque. It might just be the elegant, efficient solution you're looking for.
Thanks for joining us to dive into the deque.
Yep, great discussion. We'll see you on the next deep dive.